Hi, my name is Dan, and I'm excited to share our work on decentralized online ensembles of Gaussian processes for multi-agent systems. This is joint work with Fernando Llorente and Pedro Jurich. We're from the Department of Electrical and Computer Engineering at Stony Brook University in Stony Brook, New York, and this is work accepted and to be presented at ICASSP 2025. As a brief outline, we'll begin with some motivation and notation before moving to background, mostly in Gaussian processes and the random Fourier feature approximation. We'll then talk about decentralized inference for RFGPs and ensembling of decentralized RFGPs. Then we'll move to experiments and some future work and conclusions. To begin with motivations and our contributions, we're focused on the decentralized online multi-agent setting. So this means that we want to estimate a function f, which goes from a d-dimensional input to a real output by combining the estimates of n different agents. The inference should be online, so as we receive more data, our estimates should be updated as well. And the inference should be collaborative, so different agents are trying to learn the same exact function and should improve each other's estimates. Things should also be decentralized, so we make no assumption of a centrally connected fusion center. We'll estimate the function f using Gaussian processes, which are a powerful non-parametric technique from Bayesian machine learning. Compared to existing techniques in the literature, we are the first to address this decentralized and online setting in a Bayesian way. We do so with relatively little communication overhead, and we recover the centralized result with high accuracy in our experiments. We also recover the centralized result exactly in the limit of infinite communications. For notation, we'll use f to be the function to be estimated. We'll assume that there are capital N agents and that the agent an may communicate according to a weakly connected and undirected graph G with neighbors n and edges e. So the neighbors of agent an will be capital N lowercase sub n. We'll also assume that data arise online with agent an receiving the datum xnt, ynt at some time t, which goes from 1 to capital T. Now we'll move to background. So first, the setting in this work is Gaussian processes. These are a flexible and non-parametric tool that have become a standard in Bayesian machine learning. We can define a GP using the mean function, mu of x, and the covariance, or kernel function, kappa. The mean function, which is usually taken to be 0, is our prior guess at the function, and the covariance function tells us how related two inputs should be. A useful mental model is that GPs place a prior over paths, and by paths we mean these lines over here, and therefore they form a prior over functions. The shape or the smoothness of these functions can be controlled by the covariance kernel, kappa. In general, for GP-based models, we assume that the observations y are some noisy observation of the GP f of x. So we place a GP prior on f of x and then receive a noisy observation. If the noise epsilon is Gaussian, the posterior is another GP. We have a conjugate situation. The posterior predictive can then be computed using various covariance matrices. One main limitation of GP-based inference is that we must invert this n by n covariance matrix, where n is the number of data points that we've received. This scales poorly with the number of data points and can become intractable quickly. Thus, there's been a lot of attention at approximate GP inference. One common method are called random feature GPs. So for a stationary GP, so a GP where the kernel depends only on the difference of the two inputs, we can represent the kernel in the spectral domain via the Wiener-Khinchin integral. The random Fourier feature approximation then takes a Monte Carlo estimate of this Wiener-Khinchin integral and knows the symmetry. By taking j over 2 spectral frequencies, we then obtain a linear model through this Monte Carlo integration. We have an example below of the exact GP and the random Fourier feature GP, where the approximation is not perfect, but reliable enough for many applications. Since the RFGP provides a linear model, sequential or recursive learning is possible by standard common filter updates. We therefore obtain constant time updates with order of j cubed computation rather than the data points. So what do we mean by that? We receive one data point, we update a function, we receive another, and then we receive a whole sequence of data points. We want to update our posterior predictive after each datum is received. Now we move to distributed GPs. So we begin our distributed approach with the simplified case of having a fusion center. We'll move to the decentralized case after. Our approach works by combining the subposteriors of each local agent. So each agent collects its data, comes up with its own likelihood innovation term, and we will pool all of those together to define the full posterior. In linear Gaussian settings, the updates to the posterior are actually additive, not in the mean and the covariance, but in the related information quantities. So we have the precision matrix P and the information vector S, which is formed based off of the precision matrix and the mean. Thus, we can obtain the full posterior at a fusion center by summing up all of the P and S terms. We thus obtain information quantities D C of t, so D of the fusion center at time t, and eta C of t. What does this look like in a schematic? Well, each agent comes up with its own information quantities, P and S, based off of its local mini batch of data, and then communicates that into the fusion center, which updates D and eta accordingly. For a decentralized approach, we'll consider additive consensus. So additive consensus allows us to, in a decentralized way, without a fusion center, obtain the sum of some quantities that are local to each agent. It allows us, with an iterative procedure, to converge to the exact sum. This works by taking local averages, so we do what's called average consensus, and then multiply at the end by the total number of agents. Even for directed graphs that are simply weakly connected, additive consensus converges to the correct quantity if we choose the weighting accordingly. What does this process look like? Well, we have the true average in this case in the middle, and each agent starts off with their own local estimate. What they will do is iteratively communicate only with their neighbors, depicted in the graph by lines, and then eventually converge fairly quickly to this singular average quantity. We can obtain the sum of these quantities then by simply multiplying by n, in this case 5. So our decentralized learning uses additive consensus to obtain the correct innovation quantities without a fusion center. Thus, we proceed with L steps of additive consensus before updating the posterior. For simplicity, we use local weighting, which is sufficient for an unconnected graph, or for undirected graph, sorry. So the updates are quite simple. They are simply local averages. So again, what does this look like? Well, let's focus on agent 2 in this case. So agent 2 is connected only to agents 1 and 4, who come up with their own information quantities, P1T, S1T, and P4T, S4T. Then they communicate to agent 2, who then, along with their own information quantity, P2T and S2T, update their average accordingly. Then, at the next step, agents 1 and 4 take their consensus quantities from their first step of consensus, communicate those, and we again obtain another update. After L total iterations, we then multiply by n. Now we have difficulties in this setup with hyperparameters. Hyperparameters can be quite influential and determine the covariance function. In order to keep the nice and closed form recursive updates, all agents must use shared fixed hyperparameters. Changing the hyperparameters for the RFGPs destroys both the closed form information filter updates, as well as the consistency of the consensus estimates. In the current work, we therefore study an ensembling solution. Recent work in the online GP literature uses Bayesian model averaging to combine these models. So at each time step, the weights of each model are chosen to be proportional to the weights at the previous time step times the predictive likelihood. In the decentralized setting, this is unfortunately difficult because we essentially must make an estimate of the marginal likelihood in a decentralized fashion. Unfortunately, the factorization of the marginal likelihood does not quite work out, and therefore we introduce two variants with different approximations for the decentralized online BMA. First is local BMA, where online BMA is performed on local data only for each agent. And the second is independent consensus BMA, where BMA is performed via an independent approximation across agents. This is a fairly common approximation used in the distributed GP literature and essentially corresponds to each agent observing data that is dissimilar enough to where they don't enter each other's likelihoods. They have very small covariance. For our experiments, we compare against a set of different state-of-the-art methods in centralized, decentralized, frequentist, Bayesian, and online and offline methods for kernels. The first is MPIE, which is an offline method for distributed GP inference. The next is DOMCOL, which is a frequentist distributed multiple online kernel method. The next is Atterraker, which is a frequentist online multiple kernel method. And the last is SVI GPs. These are an efficient offline GP method that form a sort of gold standard to approximate GP inference. For all experiments, we use L equals 10 iterations with N equals 5 agents and M equals 3 models. RFGPs use J equals 50 random features. In our experimental results, we plot the running MSE, so the MSE of all data seen so far, and the MSE on holdout data that is simply the end of the data stream. Our method consistently beats all presented baselines, even offline and centralized ones, and is even comparable to SVI GPs, which are sort of gold standard as a batch and centralized solution. Consensus performs well in these experiments with N equals 1 and N equals 5 agents performing similarly well. Therefore, in the decentralized case, we are essentially recovering the oracle performance. And on the data sets presented, the ensemble of RFGPs is essentially able to recover the SVI GP performance, even on tens of thousands of data points. Our future work has several possible directions. One is a more thorough benchmarking, for example, by varying the consensus steps, varying the number of agents, the types of graphs for the communication, and so on. Another is introducing decentralized hyperparameter tuning. And another is applications to real-world use cases, as well as Bayesian optimization. In summary, we introduce a method for online decentralized learning with Gaussian processes. We accomplish this with a distributed information filter and additive consensus algorithms. And our experiments show competitive performance with respect to offline, centralized, and frequentist benchmarks. Our paper is available on IEEE Explore or for free on the archive. Our code is available on GitHub, and our poster will be on Thursday, April 10th from 2 p.m. to 3:20 p.m.